Hello, everyone. Welcome to that session. That's the last one for the day, and before the TechFest party as well. I hope that you guys are looking forward to it as much as I am. I'll be there. My name is Emil Velinov. I'm a program manager from a team in Redmond called the Windows Azure Customer Advisory Team. I actually happen to be based in New Zealand, and I look after customers in APAC, basically, with the major focus being on Australia and New Zealand. The Customer Advisory Team is actually part of the core engineering team in Redmond. So we are not part of services, we are not part of the marketing organization. And the idea is that we, being deployed out in the field, so to speak, engage in customer projects to understand what people are doing, to understand what is working and what is not working, more importantly, for those new services that we are releasing. And we basically bring that feedback back into the development teams so that they can work on those gaps or bugs or whatever the issue is, and ultimately the technology gets better. And it supports the specific requirements that you might have. So since I'm not part of services and since I'm not part of marketing, I actually come into a project for free. As long as we as a customer advisory team, the whole group, believes that that project is going to generate some interesting learnings that the technology can benefit from. So if you believe that you have interesting large projects, challenging projects, high volume of transactions or whatnot, bring that to my attention. It will go through that triaging with the CAT team, and then if we think that it is a good project for us to engage, the whole CAT team effectively through me becomes available to your project to help out. We are not delivery people. We are there in advisory capacity in a way, being part of the customer advisory team. All right, with no further delay, let's jump into the session, which today is going to focus on optimizing performance for SQL Server running in Windows Azure virtual machines. So to be very, very clear from the beginning, this is not a session that is going to look into the optimization techniques within SQL for your specific solution. Index troubleshooting and all that sort of stuff. This is outside of the scope of this session. It really is focusing on giving you solid understanding of how to leverage the Azure platform as the runtime platform, effectively as the hosting platform for running SQL Server in a VM deployed to that platform, because there are a lot of subtleties when you compare that to a local data center or even to a local virtualized data center or VMs running locally on Hyper-V, for example. So the first thing that I want to highlight is that the engineering group, along with team members from my group as well, from the customer advisory team, we delivered that white paper called Performance Guidance for SQL Server in Windows Azure Virtual Machines, which happens to be identical, the title happens to be identical as the title for this session. A lot of what you are going to hear today here is effectively derived from that white paper, and it gives you just the most important items that you need to understand and pay attention to. So I highly encourage you, even after the session, to go download that white paper and have a quick read through. It's about 40-50 pages long, but it's time well spent. So performance tuning. How do you know effectively what you need to tune and when you've tuned it to whatever is possible out of the platform? So analyzing performance impact, right? There are two things. The first one is your application design, such as queries that haven't been optimized correctly or are missing indexes, or that classic SQL side of optimization. Or is it a problem with how I configured the platform, how I'm deploying my virtual machine on top of that shared cloud infrastructure effectively? So there are a bunch of buckets, if you wish, of understanding and tuning performance. So we start basically with the platform characteristics. The first step there, of course, is knowing what the platform characteristics are. And the second step is, okay, now that I know what the platform can give me, am I, fitting with that frame effectively that, in a way, I have to play with. Best practices. Okay, having some characteristics in the platform is fantastic, but how do I utilize that knowledge to configure that platform in the best possible way? Monitoring is important, as we all know. And on top of what stock standard SQL gives you in terms of monitoring techniques and tools, in Azure you also have some additional options there that you need to consider, because monitoring around those additional options also reflects on the performance ultimately of your SQL workload. And finally, of course, is troubleshooting. How do you know where to troubleshoot, which relates to monitoring, and what can you do to troubleshoot? So KPIs for SQL. How do you measure what you are getting out of SQL Server? And this is really 101 stuff. Throughput and latency. Ultimately, those are the two things that you need to consider. And when you look at those, you also need to understand what is the SQL workload that you are running, right? Is it an OLTP system? Is it a data warehouse? The log itself comes with a workload pattern that is log specific as well. So you need to understand all that sort of stuff. So read-write mix, as we all know, for OLTP, it is mostly reads. They're small in size, 8K blocks, whatnot. And usually they come in very, very high amount, right? Data warehouse, scan intensive, sequential, right? Same thing for, for the log, of course, it requires low latency for OLTP workloads. The pattern, the I/O pattern for data warehousing, large blocks, right? We all know that. And the log, highly sequential. Number of users, that's sort of obvious as well, so I'm not going to go into this. So with that in mind, we need to now somehow relate some of these metrics to the platform. And I'm sure that you've heard a lot of Azure-related stuff already. What we are really going to focus on within this session is understanding a little bit deeper the storage system and the storage characteristics, because ultimately, this is one of the biggest bottlenecks for a SQL Server deployment, and that applies to a SQL Server deployment in infrastructure as a service running on a virtual machine. So if we peek into the infrastructure as a service architecture, starting from the regional level, this is basically a particular geography. Let's pick Australia, which very soon will have 2 data centers. Those 2 data centers, they are going to sit effectively in 2 regions. One of them is going to be in Sydney or around Sydney. The other one is going to be in the Melbourne area, right? So you are going to have 2 regions. Initially, each one of those 2 regions is going to have 1 data center. One region may have multiple data centers. And we already have that in other parts of the world, right? That's why you have a region, and then the data center is an entity within the region. And within the data center, then you have clusters, which are basically the racks that we have, or containers, whatever the actual physical deployment unit is. It really varies from one data center to the next, depending on what hardware is deployed within that data center. And what is interesting about the cluster is that it has some, the host machines, the physical servers that run within a cluster share certain characteristics together with each other, and share resources with each other as well. For example, networking is at the cluster level. you would expect that if you are having a network problem, at the cluster level, all the servers within that cluster are going to experience some sort of networking issues. Right? Why is it important to understand? Not necessarily related to performance, but related to availability. So if you are standing up an always-on availability group, which comprises of, let's say, 2 servers, primary and secondary, then you need to think, how do I make sure that those 2 servers are effectively deployed on 2 different clusters? Right? That sort of thing. So a virtual machine deployed to Windows Azure is logically hosted and owned by something that we call a cloud service. And the cloud service is the logical networking and security boundary within the Windows Azure environment. So a cloud service gives you a public IP address, only one, right? It gives you a security boundary in terms of networking. So virtual machines that you deploy within that single cloud service can talk to each other, but they can't talk outside of that cloud service unless you put them in a higher level networking concept called virtual network, right? So it is a security networking and visibility boundary in a way, and the virtual machines live inside. You can have a cloud service that is completely empty, so you've just logically defined that you are requesting some sort of container for virtual machines. You can deploy one virtual machine, or you can deploy multiple virtual machines, as part of the same cloud service. Now, based on what I said just a minute ago, all the machines that reside within that cloud service will be sharing a single external IP address and URL name or DNS name effectively. So you need to think about how you are going to route traffic, or whether traffic needs to be load balanced across all these machines. Which basically leads us to the networking view of a cloud service. So there are 2 access patterns in terms of network routing from outside that cloud service into resources that run inside the cloud service. The first one is the load balancing pattern, whereby you define that traffic that hits that front-end load balancer that exposes the public single IP address in front of all these machines. When traffic hits that load balancer, it is going to be distributed in a round-robin fashion across the multiple virtual machines. And that starts looking like a web farm, really, if you think about it. Or the other communication pattern into the cloud service, and the communication patterns can be mixed and matched, is what we call port forwarding. So if on all these VMs that you have inside that single cloud service, you have remote desktop running exposed on port 3389, right? When 3389 traffic hits the front-end cloud service single IP address, how do we know which back-end machine to go to, right? And the answer to that is that you can register basically different ports on the front-end load balancer on that single IP address, and depending on which port you are accessing at the front end externally, traffic will always be routed at the back end to port 3389 to whichever VM corresponds to the external port that you have running on that load balancer. So this is the port forwarding. If we look at the inside, so to speak, of a virtual machine, you have obviously the guest OS executing on top of hypervisor. And then there is a bunch of storage that this VM needs in order to be persistent. The first disk that it needs, of course, is C drive. This is where the operating system is deployed. And C drive itself is ultimately stored in Windows Azure Blob Storage. So this is the very first thing that we need to understand when we start thinking about performance. the operating system and everything else on C drive is effectively routed to Windows Azure Blob Storage. How many of you know how Windows Azure Blob Storage is exposed to whoever needs to work with Azure Blob Storage? No? So it's a public service. All the storage system, Windows Azure Blob Storage, is exposed as public API. Authenticated API, of course, to access only your entities that you store in a blob storage. But ultimately, it is a REST API. It is, HTTP, REST HTTP. When you put a virtual machine, did I click forward? Yeah. When you put a virtual machine and C drive is stored in the cloud storage system, effectively every single thing that the VM has to do in terms of disk I/O needs to go through that storage API in order to be persisted in the storage system, right? Now, there are a bunch of optimizations, of course, that we've implemented in the platform. And the first one that is of relevance here is the caching. So obviously, the OS is, I/O dependent. And the workload pattern for the OS is intensive reads. So we have read cache implemented and available for the system drive, for C drive. So despite the fact that it lives in Azure Blob Storage, it is accessible via the REST HTTP API, right? For frequently accessed data, we are storing that locally. And we are storing that in two locations. The first location is in the direct attached storage to the host hardware, and then also in the memory as a tier 2 cache of the host as well. Why do I keep clicking this? Right. So the second thing that you are going to get as part of a VM in Azure is a D drive. And that D drive is called a temporary drive. We'll talk about that a little bit later. But what you will notice in that picture is that that drive doesn't go to Azure Blob Storage. That drive is only, effectively only persists the data to locally attached storage. You are immediately thinking, oh, that's got to be fast, right? And you might be right, maybe not. But there are some terms and conditions apply when you start thinking about leveraging that local D drive for certain workload patterns. And then you have custom data disks. You can have multiple data disks. Each of them is physically stored in Azure Blob Storage as well. And you are in control when you provision a new disk, data disk, you are in control what caching policy you want to apply to that disk, starting from no caching whatsoever, being the default. Then you have read-only caching or read-write caching. To take the read-only caching scenario, for example, when you are accessing a piece of data, the very first time, the environment will need to go to the file effectively that is stored in Azure Blob Storage. It will retrieve the data. It will cache it locally. And then the second time that data is accessed, it is going to be served out of the local cache instead of consuming the public blob storage API once again. And I keep on switching and switching. All right. So this is pretty much what we've covered, I believe. The only thing that I want to say on this slide beyond what we already discussed is that for data disks, which are persistent, it varies how many you can have on a single VM. And it's dependent on the size of the VM. We have a number of different VM sizes that you can choose from at the time when you provision the machine, or you can upscale the machine after the initial provisioning process. So in other words, you can start out with a medium-sized VM. We'll see what that is in terms of characteristics in just a second, right? But then in 2 weeks' time, if you realize that those resources are not enough, you can upscale it to an extra large, which comes with a different set of resources, obviously more than the medium size. Good. Let's see. Is there anything else? Oh, all these disks, the OS disk and the custom data disks that you can provision, effectively they are VHD files that get stored in Azure Blob Storage, right? Stock standard VHDs. You can provision them on premises if you want, then upload them and attach them to a VM, or you can provision them directly in the cloud against the running virtual machine. And in fact, depending on how we go for time, I may show you a very quick demo, sort of out of band, how to do that. So on the next step, very quickly, the characteristics of the different sizes of VMs that are available, starting out from extra small, going up to the high memory VM sizes, which is A6 and A7. Extra small is not really applicable to databases, so forget that, right? If you are testing some web app or a web service or something like that, yeah, but for databases, just ignore it. And then the most interesting part here is if you look at the last column, no, the last two columns actually. The second last is maximum data disks, right? Each disk can be up to 1 terabyte big, right? For a small instance, you can attach two data disks, so you end up with C drive, D drive, E and F, and then you go by 2, up to 16. So extra large can have up to 16 1 terabyte disks, right? So our target and commitment is that we are going to give you at least 500 IOPS per disk. Right? That's interesting to understand, because if you need more IOPS, you need to do something, you know, beyond just here is the disk, store the data on it, right? And by the same principle, ultimately, the highest IOPS that you can get is 16 multiplied by 500. So that's what, 8,000? Yeah. Cool. So VMIO subsystem, it's important to understand. OK, so here is the thing. That's similar to what we discussed in a way, and I sort of jumped ahead a little bit in the content. What I didn't say is that the storage, or wasn't at least clear about it, is that the Azure Blob Storage is a shared service. I sign up and do something with it, as in storing data. You sign up and you start storing data. Someone else signs up and starts storing data. And depending on, you know, what the usage pattern is, you may experience, you as an individual tenant consuming that service, you may experience these variances in the performance. So if today you read, you know, 600 IOPS from your data disk, for example, and you run exactly the same workload tomorrow, you may find out that you are getting 1,000 IOPS. Or you may find out that you are getting 550 IOPS. Right? But count more or less on the 500 IOPS. Right? Because this is what we are aiming for to support in terms of performance. Good. So in terms of data redundancy and high availability, the Azure Blob Storage system internally has built-in high availability for the data. Right? So it's built on top of commodity hardware. So we have multiple nodes by the thousands, physical nodes that store data. Right? And when you access the API to store a piece of data in that storage environment, it effectively goes to 3 of these nodes, not just one. If one of those nodes, being a commodity piece of hardware, falls apart, CPU burns, whatnot, right? You are left with 2 copies. The system will detect the fact that the third replica internally has failed and is not available, and it will reprovision a third replica from the 2 that we already have running. So you are protected against hardware failures effectively. And that gives you higher availability, of course. Okay. Caching, we already discussed caching and how it works, and that we have 2 tiers of caching. This is the actual architectural diagram for the caching system, right? On the far right-hand side, you have the cloud accessible via that API that I was talking about. Then you have the host running hypervisor, and then you have the guest OS inside, right? Then C drive, as we discussed, is backed up by 2-tier cache approach. Tier 1 goes to the local attached storage. Tier 2 cache goes to the memory of the host. And then D drive is directly attached to the local storage. Your custom data drives, again, depend on what caching policy you choose for those. So when you choose a caching policy, you need to understand also one other thing, that that host is running other tenants' VMs as well, not just your VM, right? And depending on how intensive those other workloads are and how they are leveraging the cache, again, your performance might slightly vary, right? So don't expect complete consistency in the performance that you are going to get from a VM running in that shared infrastructure. So we already spoke that you have the OS disk and data disk. The OS disk by default does not support no cache option. And the reason for this is because the OS really runs best with read-only cache. Was it read-only or read-write? Yeah, read-write actually, sorry. So this is the default option that you get. You could potentially change it. It's not advised because we've done extensive testing internally that shows that C drive has read-write. The read-write option is the best performance. This is important because there is later on a piece of advice around small databases and their performance. And I think that you can guess what that piece of advice is going to be, or best practice, if you wish. For your data disks, you have all the options available, of course. I'll only give you a best practice that is on the slides a little bit later on, but I'll jump into that. For random access patterns, such as OLTP workloads, don't enable cache, right? Go directly against the, effectively the Azure storage tier, because it's highly scalable, so you can put large volume, of transactions against it, at the cost of a slightly increased latency, because you need to go through that API tier, right? For data warehousing workloads, quite the opposite. You can, or at least you can consider enabling read-only cache. Not read-write, read-only cache. Okay? So that takes us to the best practices. And okay. Wait. Okay, we went to best practices, cache settings, single disk. All right. So when we start looking at a single disk, those are the 1 terabyte drives. What can we expect? And the message is, which is validated through customer workloads that we already have running in the cloud, that for tier 2 applications, it actually gives you good performance. I'll do a very quick poll. We discussed that, from a single drive, you can expect about 500 IOPS or thereabouts. How many IOPS can you get from a SAS disk, for example? Give or take, just give me a rough number. What do you think? 120? That's a good guess. That's in the ballpark. I mean, you could go up to 180-ish, 200 probably, but that will be pushing it. So in a single disk, you have 2.5, 3 times the single Azure disk. You have 2.5, 3 times the IOPS that you can get from a single SAS drive, for example. That's not too bad, right? Bandwidth is a slightly different beast, right? So our test basically showed that for random I/O patterns with 8K blocks, you can expect around 4 megs. And again, don't take these numbers as clear-cut, because if we test, which we are going to do just in a few moments, we may get 3.8 or we may get 6 or 7, right? If the system is at the moment not too busy or, you know. But more or less you can expect that. You can see how that progresses to sequential IOs with different block sizes as well. We have actually, the next slide will give us you know, some of the statistics for multiple disk configurations, which is what we are recommending here. So if you have, there are 2 scenarios. You have data volume that is bigger than 1 terabyte. What do you do then? Because a single disk can go up to 1 terabyte. Or the IOPS that a single disk gives you are not enough for your workload. This is when you start thinking about you know, stitching multiple disks together somehow with whatever technology is available to you. And there are really 2, 2.5, 3 options, depending on how you look at it. The first one is at the SQL level, right? You can basically do multiple data files that support a single database, and you can put through the SQL configuration those data files, spread them across multiple disks. And then SQL, as a process, becomes responsible for spreading the data and therefore leveraging the increased IOPS from you know, the aggregate power or the aggregate IOPS numbers that those multiple disks can give you. So that's option number 1. Option number 2 is to go to the OS and say, please OS, create a striped drive on top of multiple data disks that I attached, effectively provisioned and attached to this virtual machine. And the other half option, or third option, again, depends on how you look at it, is if you are using Windows Server 2012, then you have the storage spaces, which is striping on steroids in a way, or a slightly different implementation of striping. That has proved to deliver better performance than the classic striping that we know from you know, Windows 2008, for example. So again, if you are deploying on 2012, Windows Server 2012, and need to stripe the data or stitch multiple disks at the OS level, then consider the storage spaces. Why? So we said that, you know, it's better to use the SQL level striping. Why would you be using OS striping? I hope that it is not there, or maybe it is. Any good reasons? Why would you go to the OS? For an existing database, yeah, that will be true. That's actually the answer that I was looking for. Yours is absolutely spot on and valid as well, but that's in that context, that's the one that I was looking for. So if your log file requires more IOPS than what a single disk can give you, you can't have, you know, the log file spread across multiple OS disks, and therefore you need to create a single OS disk using striping. Good. All right. So if we start looking at what we can expect out of a multiple disk configuration, and again, this is now irrelevant whether we are using, you know, SQL striping, so to speak, or OS striping. This is what you can get with 4, 8, and 16 drives. The interesting observations that one can come up with here is that if we look at the first column or the first pattern, which is random I/O, it's extremely linearly scalable, right? You just add disks and the IOPS just go up. And same thing goes for the throughput. It's linearly scalable. If you look at the large blocks access pattern at the end in the last column, not so much. So keep that in mind. It's very, very interesting. All right, so let's do a quick demo. Red button, they say. Okay, I push the red button. Cool, all right. So this is an Azure VM that I have. I've already provisioned. It's called SQL 14-1. It used to be part of an availability group, and I'm currently on the dashboard of that virtual machine. Right at the bottom of that dashboard, I can see from Azure perspective, from platform perspective, how that machine is configured with data drives. How those data drives are leveraged within the OS in that running virtual machine, I don't know yet. It's effectively, think of that view here that you get on the Windows Azure portal as the view of the spindles that you have to support storage for that virtual machine. And strangely enough, that's sort of how I named the files as well. If you look here, they go 0, 1, 2, 3, 4, 5. Yeah. So now, if we jump into the machine via remote desktop, I'll see that on top of those data drives, I created a simple data volume. Then I have a striped data volume, which comprises of 3 data disks. Right? Then I have one log, simple again, another log, simple, and then there is the D drive, that local temporary storage. Cool. So if we, how many of you guys are familiar and have used a little utility called SQL IO? A few, okay. In case you don't know about SQL IO, this is a test utility that Microsoft has, and you can just search online and download it, that helps you basically find out the characteristics of your storage system. The parameters that you put against that utility are basically describing the disk access pattern or storage access patterns. It runs that pattern against your storage system, and it produces some result. And we can have a look at the result. So in this case, I have a very simple script in that batch file. It first runs a write-only workload for 30 seconds as a random access pattern with 32 outstanding I/O requests, or up to 32 outstanding requests. Block size is 8, and in a parameters file, I define, what disks I should be running that workload against. And the same thing for the read-only workload. 30 seconds, 32 outstanding requests, block size is 8 again. So this is your typical random pattern, basically. So let's go ahead and modify probably the parameters file. I have comments. The only one that doesn't have a comment is F drive. So we'll be running that utility against F drive. So we'll need to wait for 30 seconds or thereabouts for that thing to complete. And again, don't shoot me if the numbers that we get back are considerably different from what we discussed for a single disk, which was 500 IOPS. This is a target. Most of the time, we are doing better than this, considerably better, right? But don't count on it. So, in fact, probably while we are waiting for this, I'll just show you a results file that I had produced from before. And that was very close to the actual target. So we can see that we had, give or take, 500 IOPS for 3.8 megabytes per second. So I think that we would be finished probably in another 10-15 seconds for F drive. That was a simple volume. And then while we are looking at F drive, we are going to launch the same test against the striped volume, which is H. Okay, so that completed. Let's very quickly comment that out and uncomment H drive, save. I'll rename this file that we just produced so that we don't overwrite it. Simple volume. Oh, gosh. All right, I'll just open it in this case, and then I'm going to overwrite it. Okay, so H drive is running, and in the meantime, we can start looking at... Okay, there we go. So this is very interesting. I told you that usually we get much better performance than 500 ops. Here it's considerably more than 500. Yeah. So for the, this is which one? The right workload. So 1600 give or take. For the IOPS, 12 meg bandwidth. And for the other one, which is the read-only workload, 2100 IOPS and 16 megs throughput. It's really good, actually. If you go back to the question of, how many IOPS you get from a single SAS drive and compare this, you can see the difference. Yeah. Yeah. Your OLTP system is going to be a little bit slower probably if it's an extremely chatty application or Exactly. Yeah. So ultimately, based on what I have seen practically done at customers, and it was funny because just recently Cordia, actually, they had a session today, tomorrow, or maybe yesterday. I don't know when their session was. Their immediate feedback when they deployed a VM running SQL Server and they tested out with that was like, wow, it's faster than my on-premises environment. Like, okay, that's good for you. but it was, in all honesty, it was faster.
How does that affect SharePoint's usage? SharePoint has a specification 1 millisecond latency.
So the question here is, how does that affect SharePoint? Because SharePoint has 1 millisecond latency requirement. It does affect it. Bottom line, it does affect it. It's not necessarily affecting the end user experience. Yeah, thank you. It's not affecting the end user experience. It's some of the backend stuff that it needs, and there are backlogs that get generated in such scenarios. But my colleagues from the SharePoint team are actually having a similar session to this. So if you are particularly interested in the SharePoint workload, then go and have a chat with them. Or at least if you don't go to their session, have a conversation in the hallway. Yeah, but having said that, SharePoint is certified to run on Azure, which includes, of course, the data platform underneath as SQL, right? So if we look at the multiple drive, is that H? Yeah, it is H. And in this particular case, it's not, there isn't much of a difference. So this is another interesting symptom that you can expect, so don't get surprised. What's happening here is that I told you that a data disk, goes to that shared storage system which comprises of multiple nodes. And those nodes, they may differ from each other in many different ways. It depends on who else is using that node at that point in time. They differ on the hardware because we keep on adding storage, underlying, physical storage to that storage platform. So you end up with different generations of hardware underneath. So depending on where my F drive is physically stored and where the drives for my H drive are, right? Keeping in mind that we are aiming for 500 IOPS per drive, and sometimes you get much better, right? We are experiencing this exactly now. The single drive is doing much better, while the 3 drives behind the stripe disk, they're probably averaging around 750 IOPS per second, cumulative giving you 2,300 or whatever the number there is on the screen, right? So, and that's why I said, aim for 500 ops. If you get much better than this, fantastic, but don't count, on that much faster experience for the end user. Plan for the slower one. Right, so the same test, I ran it this morning actually. So I showed you the single disk drive, which is 500 IOPS here. And at that point in time, this is what I was getting for the write workload. And that's what I was getting for the read-only workload for the striped volume. 1,500 or close to 1,500, which is 3 times 500, right? Good, all right. So red button they said. Okay, let's back to the presentation. Good, let's quickly progress forward. So what else affects disk performance? The storage system is not just dummy hardware where you issue an I/O request and it stores the data and that's it. There are smarts. It's a platform. It's an API, right? And the API needs to deal with the shared nature of the usage of that API. So if I come in and start hammering that storage system, and you come in and you are a low volume user, the storage system is smart and goes, oh, hold on, I need to take that low usage user and put it on a different node because they are going to suffer from that high usage user, right? Or maybe they are going to throttle me as a high usage user for a moment and direct some of that data and load respectively onto a different node. So now my load doesn't go through a single node, it goes through 2 or 3 or 4 nodes, right? So there are smarts. And while these smarts take place and the system readjusts itself to support varying workloads from varying users, right? You as the end user, you as the consumer of that storage system may experience variances as well. And a warm-up period too, right? So as you start hammering the system, you see that probably initially you experience slightly poor performance, and then the system learns, oh, I need to actually put this guy on something more decent and give them more IOPS as well. So I'm going to move them, and then you start getting really, really good performance. Actually, that's what might have been happening in our test as well. Now, usually the warm-up period is about 10 minutes. That's what it takes for the system to learn that it needs to provision you on a better, environment in a way. The question comes to us quite often, okay, so in that environment, what NTFS location size do I use? Do I leave it to the default? Do I change it to 64K? And the answer is that we've tested with all different location sizes, and the variance was within 5%. So now our recommendation now is don't bother with it, just use the default, right? Single versus multiple storage accounts. So we spoke how a single disk comes with about 500 IOPS. That's what we are aiming for. A storage account, which is the entity that holds, your data in a way, it has an allowance of 20,000 IOPS. Okay? So if for whatever reason you are consuming of that allowance of 20,000 IOPS, maybe you are running 2 or 3 VMs against it, each of which requires a lot of, IOPS, then you could potentially start thinking, okay, why don't do this? I have a single VM here. I provision one storage account, which is coming close to the upper limit of the IOPS that it can give me. I now provision a second storage account, and I put one disk here and one disk here, right? It's a valid deployment option, but it creates confusion from management standpoint. So our recommendation is for a single VM, try to stick all the disks of that single VM on a single storage account. Considering that you can only go up to 16 disks at 500 IOPS each, right? You can get 8K IOPS anyway. So there is no point of trying to spread that across multiple accounts, purely for performance reasons at that point in time. Now, if you need to provision a second or third machine, then plan it so that you provision a new storage account dedicated to that third machine, and you put all the disks of that third machine on that new storage account. Good. I'm assuming that mostly everyone knows about instant file initialization. It's just a setting at the OS level. By default, it's turned on for administrator accounts on the machine. And instant file initialization means that when you create a new file on the disk, the OS, if instant file initialization is not turned on, the OS will go and write all the size of that file in zeros to zero it out, 0, 0, 0, 0, 0, up to 100 gigabytes, for example, right? Imagine doing that against that public API that storage provides. That's going to be slow. And what is going to be slow in SQL Server, if it is slow? New databases, auto growth, backups, restore. All these operations will suffer if you do not enable instant file initialization for the account and the group that runs the SQL Server process.
Could you use a synchronous file growth and SQL Server to work around that a little bit?
Potentially, yeah. Yeah, absolutely. Yeah. Now, this, of course, instant file initialization doesn't work for log files. Just something to keep in mind. Did we cover everything here? Yeah. Is there any point of doing a demo how to turn instant file initialization on? Don't think so? OK, cool. So the next one is data compression in SQL. Use it if you can. If you have spare CPU cycles, so you are floating at 30%, for example, on average for your SQL workflow, turn compression on. It is going to eat some of your CPU to do the, obviously, compression, decompression in memory, as it reads and writes the data to the storage system. But it will save you a lot of the latency, someone asked, going to storage. And you can see how significant the actual difference is, right? It's more than 2 times in some cases, actually. Cool. So the famous question, if you had done any work already with Windows Azure Virtual Machines, shall I put my temp database on the temporary drive? Sort of makes sense, because the temporary drive is temporary and the database is temporary too, so it's all good. Historically, well, in the early days of infrastructure as a service, while it was in preview, I myself, guilty, was giving the guidance to customers to put the temp database on the temp drive. Because in those early days, that temp drive was delivering really, really fast performance. And having good performance for the temp database is important. So that was the initial guidance. Then we tweaked the platform a little bit internally for various reasons, mostly so that we are fair to all the tenants that use the service and are hosted on the same infrastructure. We changed some of those characteristics, and now the guidance is no, don't put your temp database on the temp drive. Provision a data file or data drive dedicated to running the temp database workload, right? It will be a little bit more predictable than the local temp drive. If you remember when we were discussing the topology of the disks in a virtual machine, anatomy sort of slide, I told you that the local drive did I tell you? Probably not. Doesn't necessarily have very predictable performance because it is local attached storage. And if you have a lot of tenants on that physical host trying to do work against the local attached storage, the local attached storage gives you actually less bandwidth and IOPS than if you went against the Azure Storage API, which is the 500 ops, and then you can scale it out too, right? So that's why the guidance is not there. Not to speak of the fact that everything that lives on the temp drive, on D drive, in case when the machine gets rebooted or maybe we are repositioning it from one physical host to another one, everything disappears. That's okay because the temp database gets recreated every time. But if we start drilling into this, it gets recreated by the SQL account, and the SQL account may not have privileges to write to the root of D drive. This is usually the case. So SQL is going to try to, after a restart of the machine and maybe repositioning of the machine on a different host, it will try to create tempdb on D drive. It will go, I don't have permissions, oops, right? Even though everything was working fine at the time when you provisioned that virtual machine. Yes, so you create a data drive and attach that data drive to the VM, and you position tempdb onto that data drive. In fact, if you want to go one step further than this, you create two data drives, and one of them would be running your data file from tempdb. The other one would be running the log file for tempdb, right? If you need that level of performance too. Good, so how much time? Oh, demo, tempdb contention and resolution. Okay, I think that I'm going to skip the demo. It was slightly boring anyway, because the purpose of that demo was to show you that if you kept the tempdb data and log file on a single drive, and you put certain workload against that tempdb, table types and whatnot, and unoptimized joins, then you are going to end up with contention and a lot of page latching. I'm assuming that you guys know about page latching. So as a rectifying step against that, I was going to A, dedicate a drive to the log file. That's step number one. And B, any suggestions? What do you do when you end up with page latches on the tempdb data drive? Yeah. So yes, the answer to this, and the gentleman here has said that, is you create multiple data files of equal size and equal auto-growth settings to support the temp database. It is really important. Now, equally important is to understand when you do that. And this is when you do when you observe page latches on the temp database, not just as a general, I'm going to do it. I mean, it's not going to hurt. If you provision multiple tempdb data files, it's not going to hurt you. But it really rectifies the problem of having page latches in SQL, in the temp database. And I was going to measure that using, I was going to put load with a recorded trace that I had from some previous execution. And then I was going to look at DMVs to see whether I have page latches or not. Good, monitoring. So monitoring for SQL Server itself, this is stock standard as you know it already. What the cloud platform or Windows Azure gives you at the storage level is what we call storage analytics, right? And storage analytics comes in two different flavors. Well, it is storage logging and analytics. So for logging, if you turn it on, and there is a screenshot of how you turn logging on against your storage account, you basically get individual requests against the API logged and available for viewing and analysis later on, right? Those files are available as part of your storage account. I'm going to very quickly jump here. And so if we look at my data disks of what we have been doing here, we'll see that those data disks are supported by an account, storage account that is, called EV Singapore Infrastructure as a Service, and then the fully qualified name of my account, right? So if I go to the storage part of the management here, Here is my storage account, EV Singapore Infrastructure as a Service, and I look at monitoring. We are going to see some metrics there because, so availability and things like that. Now, the metrics that you have displayed on this portal are the aggregates, or those are the analytics, which I also have turned on. And you can see some characteristics there, bandwidths in and out, and total number of requests, and average end-to-end latency for reading, that's the get blob REST API, or for putting, which is obviously writing transactions into blob storage, right? And you can see what the end-to-end latency there is. How you turn that on? You just go to the configure tab, that's for the storage account. And you can see that for blobs, I have verbose logging with retention of 5 days, table and queues, which are other storage types. I have it turned off. When you are ready to look into this, where is it gone? Cloud. Right? Okay, there is that utility which enables me to Singapore Infrastructure as a Service, Analytics, View Log. Now that utility is going to bring me down all the individual requests that I have against the storage system for a period of time that I define. And at the top, you can see that it started downloading 9 out of 1,000 log files at the moment. Right? And then you can put that into a database if you need to and do analytics that you want, or you just look at the aggregates through the portal, which we have already seen. Okay, so why would you be interested in this? Correlate performance that you have seen, performance degradation that is, that you have seen in SQL with possible issues with the storage system in the cloud, potentially, right? You may start observing slightly higher latencies here, and then you'll know, oh, okay, so it is actually not just my implementation, but part of the troubleshooting. Cool, back to the slides. Next, this is basically the portal and the metrics that you can get through this. In here, you can basically do two things. Against virtual machines on the dashboard, you can look directly at performance counters for that machine that is running in the cloud. You don't need to remote desktop into the machine or anything like that. Or for storage accounts, we have seen how you can look at storage metrics too. Other platform monitoring tools, PSPing, that is going to give you an indication of, what's the story for, again, accessing storage, for example. You can use this utility from inside your virtual machine and ping your storage account to understand what latency you are getting. Traceroute is the same thing. SQL tools, I mentioned SQL I/O, and we have seen a demo of that. And then you have the perf metrics inside the OS as well as the usual DMVs that you have. So what are those usual metrics and DMVs? And this is sort of a high-level list of what you should be at least monitoring on a regular basis for a SQL Server installation. It's not comprehensive. Actually, that goes beyond SQL. That gives you also how to monitor the end-to-end user experience, and this is why we have the ASP or web-specific KPIs, not just for the SQL Server VM. And I think we will end here because the next slide that I had is really to highlight some of the common thinking around troubleshooting SQL, but this is really applicable to any SQL installation. It is not really specific to running SQL inside the cloud, right? So software, hardware configuration is really what this whole session was about, to give you understanding of what you can expect out of the storage system, how you can configure it, and how you could monitor it beyond what you are already doing for your SQL Server installation.
I was on the Cordia project
Oh,
tomorrow.
fantastic.
When we put SAP up, right?
Yeah.
Thanks.
I hope that I didn't give away.
And
That woke you up.
and
Hopefully not death.
the Azure system had 1/10 of the memory and half the CPU clock speed and outperformed their on-premise.
Right.
And all we could put it down to was IO. So IO was better.
So the gentleman here is from Cordia. Yeah.
Because the smaller stuff we bought in the cloud was fast.
Yeah. I mean,
Our intensive SAP operation.
for SAP, specifically for SAP workloads, because this is really what these guys have done so far, as long as you have memory and as long as you have disk I/O or IOPS.
We only bought 8 gigs of 7 gigs of memory, and they got 60 on-premise.
Right.
Faster.
All right. Good stuff.
Clock speed's twice, on-premise is twice. So they're doing an internal review, and we could only put it down to the IO, the spindles.
Yeah.
It's just quicker.
Completely agree, because the CPU that
I don't manage their hardware. Yeah, they got SAN.
it is a SAN, I believe. Yeah.
SAN virtualized, and they've got database, 2 database servers, 60 gigs of memory each, and then an app service, 24 gigs. Up there we did 7 and 7, and with the disk layout of 8 data files mimicking, but across 2 disks.
Yeah.
And there's an SGen which compiles the million plus programs, runs for like 12 hours flat out, and it was quicker up there than it was on premise, which is a really intensive operation because it has to go and read everything, you know. And they were off doing a review internally, going, what's wrong with our own thing? So like the American boat this morning, you know. But it's much smaller. It shouldn't have gone as well, and it was swapping like crazy because we just didn't have as much memory.
Yeah. The only thing, this is fantastic, and I'm so pleased that you guys are happy with the performance. The only thing that I'm going to say on top of this is that the fact that at times you are getting stellar performance, you know, unexpectedly good, is not something that you should be planning against and planning for, right? Always plan for the worst case scenario, which is the 500 IOPS. Yeah.
They were great. They were just blue. I don't know if they're in memory.
I will only say that the platform is evolving, and what you are going to get out of the storage system is also going to be changing, hopefully in a good way, not in a bad way. But yeah, I'm not allowed to give you more information than that because that will be bridging all sorts of things, and I don't want to be bridging anything. So any other questions? I'll walk around because that thing is going to do the same thing. All right, if not, then that will be it, guys. Go to Tech.